Hello, calculus fans. Let's find the area of the region bounded by the parabola y squared equals 4x and the line y equals 2x minus 4. Now you look at that y squared equals 4x and you think, wait a minute, how is that a parabola? Well, if I think of it as x equals y squared over 4, it's a parabola opening in the direction of the x-axis. It's just a different sort of parabola than the ones you're used to. Now if you want to graph y squared equals 4x on your calculator, solve for y, and you'll get y equals plus or minus square root of 4x. Then you can type in three separate graphs. You'll graph y equals square root of 4x. You'll graph y equals negative square root of 4x. And then, of course, you'll put in the line y equals 2x minus 4. Now, if we do all that, we'll get this picture. All right, so you see y squared equals 4x is this parabola that opens to the right. And then y equals 2x minus 4. This is the usual sort of line that you might deal with. So we need to find out where the intersection points are, so we'll set them equal to each other. So really, you have y equals square root of 4x, so you can square that. So since y squared is 4x, then we have to square y equals 2x minus 4. We got to be fair about these, set them equal to each other. So we're really setting y squared equal to each other. Okay, we can solve for x now. So if we multiply out on the left-hand side, we'll get 4x squared minus 16x plus 16 equals 4x. Move the 4x over to the left side, and we'll get 4x squared minus 20x plus 16 equals 0. Factor out the 4. And now we've got it pretty good. We've got 4 times x minus 4 times x minus 1 is equal to 0. So now we know what x is. X has to be 1 or 4. Now just like on the previous video, we have to divide this region into two pieces. And we're going to split it this time where the bottom bounding curve changes. So let's take a look at the updated graph. Notice that the top bounding curve is the same. The top bounding curve is y equals square root of 4x. And the bottom bounding curve, well, it's either the bottom half of this parabola or it's the line, depending on where you are. And that cutoff point happens right here, right through there, when x is equal to 1. So we can go ahead and compute the two areas. So a1 is the integral from 0 to 1. That was the first segment of the top curve minus the bottom curve. The top curve was y equals square root of 4x. The bottom curve was y equals negative square root of 4x. That cleans up as integral from 0 to 1 of 2 times square root of 4x dx. And you can pull the 4 outside of the square root, and so really we just get 2 times 2. And so this is not too hard to anti-differentiate. We get 8/3 x to the 3 halves. That's evaluated from 0 to 1. And so that's 8/3. Okay, A2, different story now. First of all, the bounds are different. We're going from 1 to 4. But now our top curve, still square root of 4x. But now the bottom curve is y equals 2x minus 4. The bottom curve is now the line. So we're doing the top of the parabola minus the line. Also, still not that difficult to compute an antiderivative of. Notice I pulled the 4 outside the square root to make a 2, and then distributed the minus sign here. Okay, so if you compute an antiderivative, you'll get 4/3 x to the 2/3 minus x squared plus 4x, and that's evaluated from 1 to 4. Put all those in, you get a big old mess like this. And this all boils down to 16 over 3. You should double check all that, work it out, make sure that that's really what you get. You should notice that 4 to the 3 halves, you think about how do you simplify that? 4 to the 3 halves is the same thing as 4 to the 1 half, all raised to the 3rd power, so that's 2 cubed. So our total area is A1 plus A2. That's 8/3 plus 16/3, so we get 8. Now, I'm not done by a long shot. I want to think about this in a different way. There's an easier approach, and we're going to look at the graph in a different way. What we'll do is we'll rewrite the functions so that they are each functions of y. So we have x is equal to 1/4 y squared. And we take this one and solve for x, so we get a function of y. We'll get x is equal to 1/2 y plus 2. So we're just solving for x, so they're functions of y. Now we're going to change our point of view. The up direction is now going to be the positive x-axis. Ordinarily, we think of the y-axis as the up direction. We know that intersection points occur when x is equal to 1 and x is equal to 4. Let's plug those back in to get corresponding y coordinates. So y equals 2 times 1 minus 4, that's equal to -2. And y equals 2 times 4 minus 4, that's equal to 4. Now I want to look at the same picture, but it's going to be with a different perspective. Right now, so I'm writing these as x equals a function of y. And now we also know the y coordinates of these intersection points. So now, when we evaluate an integral, we're going to do it as a function of y. So this is going to be a dy integral. Now we had computed the area this way. We computed the area as top curve minus bottom curve, where we think of these as functions of x. And then the bounds on the integral are x bounds. Now, since we're rethinking this so that the up direction is the positive x-axis, we're going to integrate with respect to y. So now the area is the integral from, and we'll have new bounds, it's from c to d. Now we have x top minus x bottom. So these are functions of y, so we'll integrate with respect to y. So now our top curve is going to be 1/2 y plus 2. And the bottom curve is 1/4 y squared. Now we only need a single integral because the top and the bottom bounding curves don't change. And our bounds on the integral are y equals -2 to y equals 4. So the area is the integral from -2 to 4 of 1/2 y plus 2 minus 1/4 y squared dy. A single integral will do because the top and the bottom bounding curves don't change. Remember, we're thinking of top and bottom, up and down, as being different. The positive x-axis is up. And this is actually a fairly straightforward integral to evaluate. We get 1/4 y squared plus 2y minus 1/12 y cubed, and we're going to evaluate that from -2 to 4. Plug everything in, we get this giant mess, and this will all boil down to 6, which is the same thing that we got before. And you should double check that. Make sure that that all works out to 6. This computation is much simpler. The top and the bottom bounding curves don't change. And I'm putting top and bottom in quotes because, again, we're thinking of up as the positive x-axis. And since they don't change, we only need one integral to compute the total area. And regardless of how messy you might think this all is, really, this is a very straightforward integral. There's nothing complicated about this. There's no parts needed, no trig substitution, no ordinary substitution, no partial fractions, none of that mumbo jumbo. We just need the power rule, and that's it. Okay. That's all for now.